Okay, I guess we are live. Hello, everyone. I am Francesco, and today I have a talk of around 2 hours. Will be me talking about algorithmic bias in AI. So just give me 1 second for sharing the screen. Okay, you should be able to see my screen. Is that correct? Like, do you see my screen? Like, do you see my slides? Okay, perfect. Okay, so we can start. So I'm Francesco Fabri, and today my talk will be algorithmic bias about AI. So will be a pretty, let's say, general talk. I will try to dive deep into a lot of concepts. So will be pretty intense. And so please stop me at any time for questions, curiosity, comments, anything that you may actually ask me in the chat. So who am I? I'm a research scientist in Eurecat. I am going to graduate also as a PhD student in Pompeu Fabra Universitat in Barcelona. And so during my study, I've been basically, during my spent time doing research in algorithmic fairness, algorithmic bias, I've been working in topics related to fairness, explainability, and privacy. And specifically, I've been doing many different things around recommender systems. So the technologies, the connected to algorithmic artificial intelligence that help us to engage a personalized user experience on online social platforms. So my work, let's say, connects pretty much to everything that relates to algorithmic fairness, algorithmic discrimination also, and recommender systems. And this is briefly me. So I've been starting a PhD in a long time ago, 2018. And I've been doing experiences outside, and since January, I'm a research scientist at Eurecat, which is a technological center in Barcelona and Catalonia. So this is briefly like most of my contribution to the research field, and I will explain a bunch of them today. So what the talk is about? So the talk is about, as I said, algorithmic bias, which is a pretty huge umbrella. And I will stick to, let's say, 2 parts. I will try to give like 45 minutes for the first part, when I will give you an introduction about the topic, also examples of how this topic relates to like how biases are meant to be related to artificial intelligence. And I will show also fundamental definition of this field. And then I will connect those with bias in rankings and recommender systems. So I will start from pretty general definition in machine learning, and then I will connect those to rankings and recommender system. In the second, then will be, let's say, I will leave 15 minutes for Q&A. Also, as I say, you can stop me at any time during the presentation, but also I will leave the last 15 minutes for discussions. And then the second part will be, I will dive deep into some papers we had the chance to publish and work on that related to bias with a specific focus in rankings and recommender system. And I will bring specifically 2 different applications. One will be in people recommender systems, and one will be in what to watch next recommendations. And then I will conclude with, let's say, wrapping up what we saw today. So let's start. I guess we can start. So as I said, first part will be introduction and algorithmic fairness in AI. So the question that we try to answer today, or we try to understand, is the following, which is like, can we trust the decision made by a machine? Which is a pretty, let's say, tricky question, which is something that we used to not think about it many years ago. But recently, like, this question has been posed because many examples has been raised by society and industry as an important component of our daily life. Specifically, each day that we use artificial intelligence that involves human beings, this is the kind of question we end up asking. Specifically, like, these are the sub questions, right? So we can actually ask: is this algorithm fair? Is it easy to understand, or did anyone tamper with it? Or specifically, is it accountable? So these kind of different questions are really general, okay, but can try to give you an overview of what does it mean asking an algorithm to be fair or to be accountable and by a human being. So this is sound pretty abstract, probably. So I will try to give a bunch of examples. So most of the literature came out with a huge case about ProPublica, published by ProPublica. This newspaper analyzed what is a recidivism tool used in US for evaluating the possibility of recidivism in candidates that had a previous experience with crime. Specifically, they wanted this tool that has been devised in US wanted to give a score of low or high risk for being of recidivism of individuals. And then what they found out that was that this tool, this machine, was actually discriminating based on the color of the skin. So based on the race. As you can see here in an example, even if the criminal records are pretty different, or you can actually see that the high risk comes from a black skinned female rather than a white man. So this kind of, let's say, this kind of example gives you a feeling of what does it mean being discriminated by a machine. So another example is there was a famous scandal coming out from Amazon. There was a team developing a tool for automatically scraping CVs of individuals applying to the jobs in Amazon. So the idea was to filter out the huge amount of CVs coming to the applications of jobs at Amazon to filter out only the good profile. So what happened there, where they found out that this tool was discriminating the individuals, they was discriminating the women applying to the job because the data that they've been using for training their model was basically 10 years of CV collected in the past. And Amazon, being, let's say, a company in the tech field, was having in their source data, in the data of the CV they collected in the last 10 years, a huge bias when most of the people were men. So like there was a STEM bias when, like clearly that in the past is something that we've been fighting, but it's still a problem. So that there is a huge predominance of male profiles in the STEM field. And this actually, as I say, reframed in the output of this tool. So this recruitment tool, what it was doing was filtering out always men. So at the end of the day, it was removing all the women in the final subset of candidates. Another example is you can actually test yourself. I don't think it still works because I think they fixed it. But in Google Translate, if you try to translate some specific words which have double genre, right? So as a doctor in English, which doesn't stick to any female or male declination, when you translate it in Spanish, now actually you can find a double translation. But many years ago, not many years ago actually, 4 or 5 years ago, you may have actually found out that there was only doctor and not doctora. And this actually, the other side, like the other side of the coin was that if you may actually put some specific categories that will stick to biases in the distribution for women, will have a natural translation for women, not for men, like for example, nurse. So this example shows us that stereotypes that are included in the input data are then affecting the final output in the algorithm, right? So what the algorithm does is just embracing the stereotypes and boosting them. So being, let's say, more hard in exaggerating those stereotypes. So this is probably one of the most evident cases of discrimination. As you can see, this is Google Photo. Okay, so and what Google Photo does, as you may know, what used to do was automatically labeling images that you were uploading on there. And so as you can see here, there's something wrong, right? So is able to tagging airplanes, cars, and bikes, when it comes to black men is coming to give the label of gorillas. And this is a clear form of how the pipeline, the whole pipeline designed for labeling photos is clearly biased, is clearly discriminating a minority, which are the black men and women. So just dropping by, I will try to drop a bunch of definitions that will be useful along the talk. So specifically what we've been talking now, so what we are talking about race, gender, age, those are actually demographics, and we can talk about those demographics as attributes, and we can define them as protected attributes. So looking at partitioning a population of individuals, we can partition some of them by demographics, and we can claim that some specific demographics, which can be a minority in our data set, can be actually defined as a protected. So it can be by race, gender, or religion. And then, starting from demographics, we can talk about group fairness. Why? Because, like, given some specific demographics, we can actually say that some of them, we actually want that the algorithm that we use, that we implement in our pipeline, has to be fair towards all those groups of different demographics. And this kind of application, this kind of constraint is called group fairness. So the goal is that each group defined by demographics is treated equally, and is receiving a similar treatment or outcome. Then, if you can imagine, since each individual can be associated not only one demographic but many, if we start to include into the design of the algorithm all the different demographics and user characteristics, and we still want to be fair, we'll start to think about individuals and not groups anymore, because each individual will have peculiar characteristics, which will be an intersection of many attributes. So at that time, the definition will still be similar, but having let's say a definition close to the individual, not the group. So we'll talk about individual fairness, not group. Then what we have is like a pretty general definition, right? So assuming that we want to include this constraint, what we face there is bias, which is a systematic error. What is bias, right? Like, which is this definition, which is easy to grasp, but that's not, because in this context, bias is a systematic error generated by algorithm, data, or outcome. So basically, those are three components in a machine learning pipeline, and the bias can come from any of them. What we want to do, we want to remove this bias, because we know that may actually benefit privileged groups and systematic advantage in them against the unprivileged groups, which are usually the protected, the ones characterized by a protected attribute. What we do then usually is, like, assuming that there is this clear bias, so what we want to do is, like, as I was showing before in the pipeline, so there was a clear problem about, for example, the Google photo labeling Black women and men as gorillas. Like, after we found out there is a bias, we have to quantify, and that reason we need a metric, okay? So as you can see, these definitions are pretty general, and I want to stick to the fact that the concept that each fairness definition for being appropriate needs the right context. So we don't have a global definition that is good for everyone, but depending on the context, we actually find out that definition is quite different. So this was the introduction. I hope it's clear, and at any time, please stop me, submit me questions. I will be happy to answer. And so, for sticking to algorithmic fairness in AI, now we try to be a little bit more technical. Specifically, in the research field, this is a plot that may actually seem funny, but that's actually true. I mean, in the sense that the style, it looks like a little bit like childish, but there's actually real numbers. So, like, the number of papers talking about algorithmic bias and fairness increased dramatically in the last years. And so, because of the example I showed before, all the research community, but also industry, became super interested in this field, understanding which are the consequences of underestimating those problems. What I want to do here is, like, giving you a high-level overview of definitions in machine learning problems. Sticking to the fairness. So in machine learning, usually what we do, we want to do classification, we want to do regression, right? So we have a supervised learning problem. And so imagine to have a classification task, which is a standard, okay? So a binary classification, for example, we may actually be interested to have, let's say, having an algorithm A that wants to learn to predict a discrete characteristic Y, let's say a binary label, for example. We want to classify, we want to have, like, a classification task. We want to classify the final observation, like, belonging to one group 0 and one group 1. And then we have a target variable, like, we have the target variable Y then, but how do we predict that target variable? We use the input data X. Then this data X probably will have a bunch of features will be useful for the prediction, but also a bunch of features that will be demographics. Demographics means that in this row of characteristics for where each row represents a user, we may actually have sensitive attribute, as I will say, as gender, ethnicity, sexual orientation, right? So because of each time we have a task that includes, let's say, human beings as observation, we may actually find out that among the characteristics of the user we collected, there is also demographics there. And imagine, for example, for the recidivism tool, right? So in that case, we want to define a score, a probability between being recidivist or not, right? So being actually prone to commit another crime or not. So this is a classification task, right? And so finally, what we do at the end, we generate a probability, which is R in this case, the probability, so the final output of the classifier, which then we compare against Y to see how close we are, let's say, to the real outcome. And we predict, we use measure of accuracy, of precision to try to stick to the goodness, to try to check the goodness of the model. So starting from there, we can say, okay, well, which kind of fairness we can actually include in our data set, right? Assuming that we know that there are some demographics there. There are three main criteria that have been established in the field. One of them is the classical one, the pretty standard one, is the statistical parity, which is pretty simple. I would say that these definitions sticks to the fact that we want to have the same level of accuracy. So want to model to have the same probability to predict the right outcome, which in this case is Y equal to 1, for both demographics, for where the demographics here are given by a conditional probability. So the probability of generating a positive outcome, given the fact that we actually generated a positive, so like the conditional probability, given the fact that we are good at predicting that, and given the fact that we have a sensitive attribute A in the individual, we are actually able to generate this probability equal to the same conditional probability, but with different attribute B. So in this case, will be given we are trying to equalize. So including this constraint in our model, we want to find that we want to be sure that our model is able to predict the good outcome for both the demographics, for both the color of the, for example, of the skin, or this both sexual orientation, or for both genders, right? So no matter which is the demographics, you want to be sure that the accuracy is the same. Now, this definition may actually seem optimal, but it's not. It's actually the first, if it's easier, or the first trivial one you can include in your model. And what you can do next is say, okay, actually, I don't want to be conditional by the outcome, but I want to be conditional by the input, right? So negative. So what I want to be sure, I want to be sure to be able to make same mistakes together, in the sense that I care. I may actually care about the positive outcome, but what is the problem to may come out, which may come out from the mistakes. So in this case, we want to this definition is called equal opportunity, and reframe this like, I want to be sure that the probability of making mistakes is the same, which is quite different from the previous one. It's kind of let's say on the other side, right? It's kind of a little bit more complex, right? And this is called equal opportunity definition. Then we have equalized odds, which is, let's say, the one which is try to stick to a general version of the second one. Equalized odds says that we want to be sure that the probability for giving a specific outcome, no matter what, so the probability of being wrong, no matter which is the real outcome, so Y equal to the observed Y, so no matter if it's 0, no matter if it's 1, has to be equal no matter which is the demographics. As you may actually understand, this is like the third definition may actually seem the most reasonable one, but this definition came one after the other, since each like giving from coming out from different consideration. What I want to say here is that we don't have to believe that one definition is better than other. We have to, as I said before, this depends on the context. And actually, there is a mathematical formulation that proves that there is no way of meeting all the same three constraints at the same time. So as I said before, we don't have a specific fairness definition that is good for everyone. Also, because this is impossible, is it really impossible, mathematically proved, it's impossible to have statistical parity, equal opportunity, equalized odds equal at the same time. So we can't achieve those three together. That's why it's called the impossibility theorem. That's why we stick to each definition depending on the context. And this, as I said, is still in classification. We will see later that in recommendation is completely another context. So what we were talking here was we're talking about, as I said, the fairness depending on the context. We need a comprehensive set of fairness metrics. And also because these fairness metrics will be useful then for either characterizing or mitigating the outcome. But then the question is, okay, but where do I mitigate this problem? Okay, assuming that I do feel there may be something wrong in my outcome, what do I do? Well, this definition, this consideration, this question is not trivial, as you may actually see from the fairness, and every layer is like, you know, some easy to treat. Is not, the solution is not straightforward. So assuming that you have this huge pipeline in machine learning, right? You start from having this raw data on the top left, when you have, you check, you know, you can check for discrimination in the preprocessing, but you can, then you train the data, but then you have another problem there, and then you generate the outcome, and then you have another problem there. So it's like, is there discrimination anywhere, right? So it's like, what's wrong with my model? What can I do, right? From raw data to deploy, there is this huge pipeline. So specifically, what you can actually do, you may actually do step by step. And asking you the following question is like, is discrimination potential at data level? So is discrimination coming from the input data? Is it something that you can actually observe and characterize in input data even before running the whole pipeline? Depending on the answer, we can actually say, okay, there's a problem in the data. There is something wrong in the data. Let's do pre-processing. So before implementing the whole machine learning pipeline, we go through a pre-processing of this data. So we sanitize the data, removing the bias. Then we may actually say, in another scenario, we can actually say, okay, the data doesn't seem bad, like we don't really we don't see anything wrong there. And the next question which actually be is like, what's happening in the training? So we may actually find out that in the pipeline, the algorithm design is something like weak, something that is not talked like properly, right? So as for example, as the one showing before about image labeling, right? So there is something probably wrong there. It's not only about the data. So we may actually say, okay, we may actually go for the training, and then understanding that we may actually do a discrimination aware training. So it's not pre-processing, but in processing. And this comes from the fact that it's not about the problem about the data, but the problem is about the algorithm itself, the solution we included. And so we may actually include fairness inside the training. So fairness constraint that I showed before inside the training process. Then there is the third one, because you say, okay, I check my data, looks fine, the algorithm is the best possible one. It seems fine to me also the way I talked about it, because the design seems fair, but then the outcome is still something wrong. And this is specifically true for the rankings, as you will say later. And like, what does it mean? Like, what can I do? Then is like, okay, I can check the output discrimination, the treatment, final treatment in the output, and then doing post-processing. So as you can see, there are 3 different strategies: pre, in, and post. And I would say, like pretty general, there is no real, let's say, claim or definition saying that one method is better than the others. I will actually say that it's good to having an in-process method, because it's kind of pretty, like, it can help also in the case of pre-processing. And then in the post-processing, like, why the pre-processing is better than the post, because actually you may find solutions in the pre-processing that will not come out in the post. So those are really, let's say, I understand it may actually be a tricky consideration to say, but it's like, okay, this is my own opinion that come out from, let's say, looking at literature, looking at the problems I've been dealing with. And I would say that the pre-processing, along with a little bit of like a proper post-processing, may actually be useful. And so, yes, this is like the first part. So before, let's say, now we stick, let's say, to the second half, which is like bias in rankings and recommended system. So if you have any question, please feel free to drop it in the chat. I will be happy to answer, but I hope that everything is clear up to this point. And so, yes, we talk about algorithmic bias and fairness in context of ranking a recommender system. Specifically, we talk about we want to I want to challenge you in this case. Like I want to see if this may actually like it's quite different from what we saw before. Okay, it's still let's say relates to the examples that we saw before, but it's slightly different. Specifically, usually what we usually do in the case of let's say when we have a query, specifically as in Google, what we usually do, we focus on the output provided to the searcher. So what we do, we actually focus on the output generated for the interest of the user, right? So as we are users of Google, we're interested to getting the best possible result given the query. So what we do, we just look at the ordered list of items by decreasing probability. And those decreasing probability is given by the relevance, right? So Google tried to give us the best possible results, a search engine to give us the best possible result given our request, our query. So then the question is for you is like, are we, in the moment that we care about the user, are we, let's say, underestimating the role on the level of the searched one, or the people, let's say, included in the process, but on the other side of the pipeline? So the searched ones are really part of the game. So in this case, on the right, there is this simple query that you may actually run on Google. I do believe that the result you may actually find out now will be pretty different, specifically because there is a problem in the query. Can you actually tell me, like, so I don't know if in the chat or like if you're free to drop in the chat the solution, but do you actually see which is the first women appearing in the photo here? Like, are you able to spot which is the first woman in the photo? Like, do you see like there is any women in there? Like, you can tell me who is, where is it specifically? And I don't know, like I'm using the chat. Hopefully, like you're able to write it down there. And yes, like I just wanted to do this. It's a simple one. It's like if you don't see any, you can say it. But if you say one, you can tell me. Okay, the last photo, exactly, the last photo in the bottom. Okay, so it's true. Like the last photo is in the bottom. You can see is Barbie CEO, right? So when you look for CEO of a company, like no, there is no other women in the picture. Like the only one in the bottom right, exactly, is Barbie CEO. So now there's a consideration here is that, are we really, like, is that true that like most of the CEO are men and the only one you can find in the top selection of CEO in the world are women? Of course not. So this distribution is clearly biased, right? This is a clear problem here. It's a clear stereotype. Still, the problem that we saw before, clear stereotype that we are including in the society, because if someone looks for CEO in Google to find out who are them, Google will just tell you that there are no women there. There are just like a bunch of men, and then there is Barbie CEO. So as I said, Google solved this problem. It was like pretty old snapshot, but you can see it's pretty like fun, I would say. I'd also say that now, I mean, it's good that the distribution now of these photos change. I also test myself. Like I tried myself to see it's kind of different. It's not like this, but still, this was a problem, right? Because what you're doing here is just like you're not caring who is searched, not caring who is on the other side of the field. You're just giving the user the best possible result that will be loved by the user, but you're not considering who is searched, and you are discriminating women in this case, including us in boosting the stereotype in the society, which is still related to the STEM professions, as I said before, which CEO probably relates to, and most of them are tech or let's say in the STEM field. So still there is a problem, right? So still there is a stereotype there. So in general, so there was a similar work. I want to drop here the name of the paper if you're interested to dive deep into literature in the theory, but just to give you the image that given by Singh and Joachim is pretty simple, right? So if you can rank your individuals in your, for example, your recruiting tool, right? You're interested to rank the best possible candidates for the job you just posted on LinkedIn. And you rank them by relevance. So there is nothing wrong in the first bar. So for each individual, as you can see, you just rank them here in the list. You can see that the scores on the top left are the scores that they have been assigned by the tool. So the tool says, okay, I do feel that the CV of this candidate can get a score of 0.82 as the first one. Then the second one is like 0.80. Then, sorry, the second one is 0.81. Then the third one is 0.80, and so on. And then you can say, okay, there are 3 males and 3 females in the, like 3 men and 3 women in the list. It's fine for me, you know, right? It's just like, because I'm ordering that by relevance. But then if you think about the differences in relevance, as you may actually see here, is if you group the average relevance of the two subsets, so male against female, you will see that there is actually slightly difference, right? So the average, so you see that the average relevance of the two users is not that big. But then, if you can actually compute the exposure associated to each candidate, where the exposure is the position on the list, which is computed with the metric in the bottom left, you will see there is a huge disparity. So someone may argue, like, why you use this definition? Why is like the definition of the exposure is given by the position, right? Because in this case, it's 1 over the logarithm of the position, which is actually a pretty standard definition, right? It's like, you may find out that in many papers, the position bias specifically is called like this. So the way that an individual evaluates the list is given by this score. So the difference between being the second and the third in the list can actually be quantified with this score of exposure. And as you can see, there is a huge gap if you group by exposure. If you generate the average exposure by the two groups. So this means that this is clearly a problem, right? So the first one, you may actually argue, okay, the relevance is not that different. It makes sense that they are listed there. But then when you look at the exposure, the fact that they are one after the other, like subsequently, like you generate a huge gap in exposure. And as I say, increasing these, let's say, unfairness and stereotype. And which may actually feel, I may feel that in the old result, as you see, the first bar is on the bottom, even if like probably the score of the image is not that different from the others, right? Apparently. So which is the, let's say, in general, also like to give you, let's say, an overview, an high-level abstraction of what we are talking about. So in recommended system, you have the consumer on one side and the producer on the other side, which is pretty different by the other, let's say, in classification task. In classification task, the objective, the focus is posed only on a group of users, right? Say of the data set. And you say, okay, there's a unfairness in the outcome of the data set, let's mitigate it because the users are part of the pipeline. But here there is not only one side of the user, there are multiple sides. Specifically, for one side there are the consumers, so the one that are, let's say, enjoying and let's say experiencing the recommendation list, the ranking list, and on the other case there are the producers of those recommendations. So the ones that are recommended, so the ones that are part of the recommended list. So we can talk about here that multiple stakeholders at the same time, and each one has a different objective. So the fairness is, in this case, comes into consideration, being considered not only as part of, let's say, a problem of the system, but problem related to a specific stakeholder involved in the definition. That's why I like this statement by a researcher, Robin Burke, it's like the major conference in fairness, which was called FAT, but since the name was a little bit tricky, let's say not the best, the community decided to change it in FACT. So fairness, accountability, and transparency is the acronym. And like actually, when we talk about fairness in recommender system, we are on the other side of the dictum by Aristotle, right? So we should say like so in this, the statement may actually be quite abstract, but like just to give you the definition of the meaning of this statement is that usually in classification we just have accuracy and we have unfairness plugged in, right? So we have this. We want to be sure that different people are not treated differently. In recommended system and rankings, there is a huge component of personalization. So like there is no point of being different should be treated equally, because actually different should be treated differently because personalization in there. So it's not only about giving the best possible outcome, but be sure that this best possible outcome is personalized by each individual, but still we need to be fair. So what does it mean? Like, what does it mean, as I said, having multiple stakeholders in mind, personalization in mind, like, okay, one definition is not enough. Say that there is fairness in the system is not enough. So what we can actually do, we can focus on the consumers and say, we want to impose consumers fairness definitions. Or we may actually say, okay, no, you know what, like, I don't care only about the consumer, I care about the producers, as we said before. So the consumers may actually be on the other side, but if you want to include fairness definition on the other side, we will talk about fairness. And then those definitions need a proper explanation, right? So when we talk about fairness, as I say, the focus is on the consumer. The unfairness is measured as a quality of recommendations. This means that the unfairness is measured as let's say, a way to quantify if two group of subset of consumers which are in our system are given same quality of recommendation. So in the general example, we may imagine two different groups of consumers in our favorite music streaming playlist, okay, music streaming services, and for some reasons, because a minority that is actually given by a specific demographic, a minority in our streaming service may actually get bad quality recommendation, right? Bad quality recommendation in terms of playlist, in terms of next songs to listen, because, for example, they are not well represented. So imagine there is a minority against a majority, you want to generate recommendation for both of them, and one of them, it doesn't get the best quality recommendation because probably we don't have enough information, or because the other majority is much more bigger than the minority. So let's say affect the recommendation output in a way that if you measure the different level of performances in terms of accuracy and DCG, imagine whatever accuracy measure you may have in the recommended system, you may actually experience a difference in quality between the two groups. So this is fairness from the consumer side, right? So you want to be sure that to stick to fairness definition that both of, let's say, groups get the same level of accuracy. The other side, which is, let's say, the one probably the unexpected. So the one from a consumer, you may actually say, okay, this is fair, this is like reasonable to exist. But then there is the fairness, when the focus is on the attention received by the items. In this case, sticking to the case of streaming service, music streaming service, they use the classical, the way of measuring the attention is exposure. And what you may actually see is like that group of artists as actually, it may actually make sense. Some artists are much more exposed by recommendation output than others, right? But these, like, because what happens? What's happening? It's happening because probably some artists are more popular. Some artists, let's say, have more items in the data set. So there are many reasons, okay, of this source of popularity bias, as we call it. But this popularity bias may actually be a problem because so given some input data set, when there are clearly some artists which are much more popular than others, when we generate the recommendation, this popularity bias, what does it do? What does it? It's just like boosting the exposure of the popular artists, discriminating the ones in presenting less, being less popular. Being not so popular doesn't mean they should not be recommended, right? So we should stick to some definitions that may actually, of fairness or algorithmic bias, that may be helpful to diversify a bit the outcome, to be sure that all the artists are treated equally, and not that, and not avoiding that the popular artists are recommended much more in terms of in relative size, and much more in relative size with respect to the unpopular ones. So there is, as I say, differences in accuracy is the fairness that sticks to, let's say, consumers, and differences in exposure, the disparate treatment in exposure is the one for the providers, which is actually the same. That this exposure definition is something that I introduced already in the paper. Specifically, we talk about exposure as this quantity distributed along the way when we generate the along the list when we generate the recommendation output. So to close it, this combination of two definitions, which are called consumer fairness and P-fairness, together mixed and let's say trying to be included in our pipeline, are called CP fairness, which makes sense, let's say, right? So you may actually experience biases coming from different sources. So it's not only about consumer fairness, may actually be about P-fairness, consumer fairness at the same time. So that's why we introduce CP fairness in our definitions. So I left this time, let's say this 15 minutes more or less for questions. So feel free to drop any. I may actually be, yes, like very happy to answer any question. And so feel free to write it in the chat, and we can have, like, since I understand this a lot, I've been dropping a lot of definition, and so I'll be happy to answer any question at this time, or curiosity also. Is that anything that is not clear, or something that you may actually ask, because it's not clear by the presentation? I will be happy to answer. Okay, any reference? That's a good point. That's a good point. Okay, so so if we are interested in fairness in exposure, I will say that this is the seminal work, the recommendation specifically. I can actually, I may actually think to post it. So I think will be shared by, I don't know if Mattia can tell us more about it, but I think will be available for the in the website, right, at the slides. I think so. So the references specifically, I left a couple of, so each time I was trying to, for example, to stick into some introduction, so definition. So this plot comes from a tutorial, and this is a reference in the bottom. And so it's like this workflow, and also there are much more information about fairness in the other tutorial here posted. Fair information access is a tutorial pretty popular. Okay, so yeah, will be available. Nice, will be available in the coming weeks. Nice. So everything will be there. I will try to all the information you will see in the bottom are references to other resources. And later in the second part, actually, there will be all the references will be connected to the name of the papers, on the links, so you can actually know more about it. And yes, I am thinking if there is anything so this definition are pretty standard. Yeah, it's actually say like ProPublica is like the reference here in the slide 15. And yeah, like this is again another tutorial. Yeah, I'll try to include also a bunch of links in the next version of the slides. So yes, to be sure that and nothing is lost in my talk. And you can actually, I mean, you can reach me at any time, like at my email and my Twitter. I will be happy to answer any curiosity or questions even offline. Okay, so I guess we can just have like 2 minutes of break, and we can go to the next. We can start with the second part. So this is the second part. I will go through some of our work done at EURECAT, and specifically papers that talk about this algorithmic bias and fairness in the setting of recommended systems. I will be back in 2 minutes, even less. Okay, I think we can start. I'm back. And so in the next 35 minutes, I will go through a bunch of work we had the chance to publish and doing research on, and will be around recommender systems, specifically the talk will be divided, the second part will be divided in two parts. The first one will be about disparate exposure in people recommender systems. And the second part will be about radicalization, what to watch next recommendation. So it will be about still algorithmic bias, but specifically the first one will be about unfairness in exposure in recommender system in social networks. And the second one will be about algorithmic bias, so still exposure, but from the size of polarization. So how this problem can actually affect what to watch next recommendations, which are basically sequential recommendations in online streaming platforms. Okay, so let's start. In this specific, so the common connection, and let's say the common path that we will follow in these three papers I'm gonna publish, I'm gonna talk about it. That's been published. Is about like the utility, the usefulness of having graph data into the loop when we talk about algorithmic bias. Specifically, so as I said before, like ranking algorithms are this core functionality, right? In online social platform, I've been talking about Google. We will see about as an example about YouTube, Twitter, LinkedIn, and all of these social platforms can be affected, are a crucial functionality that can be affected by algorithmic bias. Specifically, if we want to say in one sentence what algorithmic bias is, not specifically, like let's say not sticking to fairness, but algorithmic bias in a broad sense, we can talk about human biases and beliefs integrated into the data or into the design of the algorithm or into the outcome, affecting the final ranking generated, which actually exacerbates inequality in exposure of the output. So when we talk about rankings, as I said, it's true that the fairness can be on the side of the consumer, but most of the time, most of the research has been done there, focus on exposure, fairness in exposure, which actually is an open problem, not easy to to address. So what I said before, I said like that probably the common, let's say, pattern you will see will be around not only recommendation in bias in data, but also the utility of thinking about this phenomena in terms of graphs. Because I will show you later, like this network structure can be helpful to understand local but global, but also global phenomena. And so I will work through three different works, the different papers, when the common pattern will be the representation in graphs. As you can see on the right here, for example, we can actually imagine to have a graph representation of the users interacting with our recommender system. For example, different users are connected through social networks because they are friends on this, like for example, Facebook, or because they follow each other, like in Twitter or like in LinkedIn, right? So this is, let's say, the most simple representation as a graph, right? So where the nodes are the users. But what about if the graph is expressed in terms of contents? In the second one, indeed, like the second graph here, the second plot, we can see that there are videos, let's say, okay? So each node here is a video, and each connection between a video represents a potential recommendation, allowing me to jump in from one video to the other. So for example, in YouTube, when we watch a video and like YouTube recommends us a subset of videos as a next content to watch, next video to interact with. So we can imagine that the edge existing in this graph is the possibility to jump from one video U to a video V. So in this specific case, the edge exists if there is a recommendation starting from U and going to V. So it means that given that I watch the video U, I can jump to the video V, then there will be an edge between those two. So as you can see, like in both cases, there are two different graphs, but like in both, like we can still represent what's going on in the platform. So starting from this, we will focus first on the user network. We will first focus on the network of users. Specifically, like we will go through three different works, and you will see that the insights that we grasped from the first two works are actually helpful for the third one. So in the first two works, we will actually answer the question about, is that homophily affecting the final exposure distributed by the recommender system? And this kind of question can be answered in two different phases, scenarios, can be answered in the short term, so understanding if generating one shot of recommendation, so we have any harmful effect on the exposure of the users, and then we could say, well, this question is not enough. What may happen actually in the long term? So we may actually answer this question looking at the long-term effect of the homophily in the recommenders. So we have the short term in the first scenario, we have the long term in the second one, and then in the third one we say, okay, well, what with the insight we grasp from these two papers can actually be useful for treating and mitigating a famous effect, a radicalization on what to watch recommendation. Indeed, we define pathways, which is a sort of long-term effect of the recommender in what to watch next recommender system, which, as I said before, are these what to watch next is the sequential recommendation. Actually in the image, I guess, is pretty clear what does it mean. So you can jump from one video to the other. And what we want to see there is that if there is any harmful consequence in browsing the video recommendation on YouTube. But no spoilers at this time. We'll show you later what I'm talking about. So disparate exposure in people recommender system. So the first two works that I've been introducing in the previous slide. So for long story short, all of them are published. All of them have been published already. So one of them I'm presenting it in a bunch of weeks, and the other two are already presented and published. So like a really recent work. This is the older, I will say, 2020. So the other two are pretty recent. This is like the older ones. It's like, so this is the first of the three. So as I say, we want to understand the effect of homophily on disparate visibility. We'll use visibility and exposure as an equivalent term here, like don't get, let's say, lost. It's basically the same. So visibility and exposure, in this case, I'll treat them as similar. And then like we'll talk about this visibility of minorities in people recommender system. So we are understanding if this homophily is actually a crucial component in this pipeline of recommendations. And it's a joint work between me, my advisors, and other collaborator, Ludovico. So how do I explain this problem? I will say, well, let's start from a really simple toy example. Assuming we have a social network in front of us and we want to understand, we want to compare those two, you could see that we can actually associate colors by demographics. So assuming that each node in these two graphs is a user, and you can actually assign demographics to each of them. So we are in this case two different demographics. Let's say the color of the node is red and blue, right? And the two graphs are pretty similar, with the only difference of these two networks is the distribution of edges of the red nodes. So blue nodes are distributing exactly the same. What is changing here is the distribution of the red nodes. Specifically, they connect in the second graph, in network B, the red nodes connect much more frequently than in the top. So in the bottom graph, you can see that the red nodes are connecting much more between themselves and not the blue ones. So what we do now, we just like, okay, we take these two graphs, we are able to running a preferential attachment recommender system, which is a really basic recommender, looking at the intersection of edges between nodes. So what we do, we generate these new edges, which are basically recommendations, right? So as you can see, for example, in LinkedIn or Twitter or Facebook, this is a typical feature, right? When you go through you are scrolling the home page, and the online social platform suggests you new connection to add in your network. So what's happening here is like we are able to generate new recommendations, which are the color, the edges here in red and blue. And what actually can do, assuming that each time a new recommendation is generated, we are actually exposing some users. As I said before, we can actually quantify this exposure, right? We can actually check how many times a user has been recommended. The interesting thing is, if you look at the distribution of exposure in the two groups, the two groups is flipped. So it means that the red ones in the first network were recommended less often than the blue. 3 against 7. And you will say, well, this is reasonable because let's say the red is a minority, or let's say that this distribution quite resemble the distribution of exposure resemble the partition of the nodes. But then if you change the edge distribution of the red node, this exposure is flipped. And in this case, the red nodes are much more exposed than the blue. Is it kind of interesting? So because like what we experienced it from one network to the other was just changing the level of homophily inside the one group. Specifically, homophily here is defined as the tendency of similar individuals to connect between themselves and not with the others. So this means that the red nodes in the second network are much more homophilic because they tend to connect with similar peers. To give you, let's say, a concrete examples, in reality, you may actually think about this node as a different age, right? So it's distribution. And you can imagine that, let's say, younger generations may connect much more often between themselves and not with, let's say, adult generation, different, no? We have Generation Z, Boomers, this kind of, and so you can imagine that if you can have a different class of individuals in the network, they may actually connect much more often within the class and not between classes. So yes, so like in general, as I said, assuming that we have different demographics distributed in the network, then we generate recommendations. And these recommendations, which are core functionality of all these platforms, are generated through an algorithm. Then that pops out in our own page. And what we say, with our assumption in the paper is there any effect driven by the homophily? Is homophily a driving force? So the question here is like, is the homophily affecting the social graph and then the final output of the recommendation algorithm? The answer is, of course, yes, as you said, the toy example. And we are trying to dive deep now into the experiments. Please, since from this moment, the talk a little bit technical, I will try to drop, let's say, a bunch of metrics. So please feel free to stop me at any time if something is not clear. If you want me to explain, I would be really happy to do it. So please write on the chat anything that you don't feel is clear at this stage. So what we did, like in this empirical study, we just analyzed a bunch of, we took like 20. For the Spanish audience will be something that they may actually know about it, which was a famous social network in Spain, was actually called the Spanish Facebook some years ago. And so given this social network, so given this data set that is available for us, we can actually split, we can actually partition the users by demographics. So we can have different distribution of minority and majority. For example, we can have a younger minority in the first 20, age 16, which is actually homophilic. So we observe that we can partition the graph having a minority really homophilic, and with the majority, let's say the older subset, with a clear weak homophily, level of homophily. Then we have POCEC, which is a Slovak social network, where still the minority is homophilic and the majority is not. Sorry, the minority is homophilic and majority is not. And let's say that there is no clear definition of minority and majority. So in all this study, you will see the two components we want to understand, let's say, evaluate are the size of the two. So how the size of the two groups affect the output, but also the level of homophily. So we have this minority majority distribution that we want to stretch, but also the level of homophily inside the two groups. So that's why we have 20 and POCEC, and we have different versions of 20, because depending on which attributes or which partition we can actually generate, there will be more or less homophilic groups, and also different distributions of minority and majority. So we will have a depopulated networks, and as I said, with which 20 and 16, there is a strong homophilic minority. In the POCEC A21, there is strong homophilic minority, which is the same size of the majority. And then there is 2830, which is a small natural minority. And then there is the 20G, which is the 20 divided by gender, and which there are natural minority and majority, but let's say this clear partition, there is a clear partition, but not as the 2830. So in each configuration, there is a specific characteristic we can observe. And so what we want to evaluate is like how these characteristics affect the final distribution of exposure generated by the recommender. Specifically, what we do, we run 4 different recommender systems on these data sets. And each recommender is representing a category. So like there is a topology base, which has atomic adder, there is a collaborative filtering, which ALS, alternating English square is called. Then there is a random walk representative, which is the salsa. The salsa, the acronym of salsa, is also was some years ago was actually the state of the art in Twitter. It means that it was actually the algorithm implemented in Twitter many years ago. And then there are a bunch of there is a baseline. Let's say the baseline is the random. So we just generate random links into the recommendations. And so yes, what do? We just like we take these 4 algorithms with these 4 data sets, and we evaluate the level of disparate exposure generated by the algorithm. So what happens here? The observation, the clear observation. So this huge table is just giving you the clear. So if you focus on the first 2 data sets in 2016 of POG K21, what you can clearly see is that disparate exposure, it exists and benefits the minority that is homophilic. So something that we saw in the toy example here is proved again in our real data set, the real world data set. Specifically, delta V is measured as a disparate visibility or exposure. As I said, are words we use equivalently, which is with this index, this metric, this bias metric. As I said, the metric is fundamental for evaluating the bias in the output. Is positive if we allocate much more exposure for a small minority, and is negative if we allocate much more exposure for the majority. Let's say that it's close to 0, and this is important to say, when visibility or when exposure allocated to the 2 groups is proportional to the relative size. So let's say that we will claim that there is no real bias problem in this context if exposure is allocated in a distribution close to the one of the nodes. Specifically here, what we can say is this, that like in the first 2, having an homophilic minority benefits, having homophility or minority in the graph generates a biased output when the exposure is allocated to the homophilic minority. But then if the minority is not homophilic and is small, as a 2830, then because SM, HM represent the size of the minority and also the level of homophily, so there is no clear, so if the homophily is close to 0, there is no clear homophily. If it's negative, it's actually the opposite. Sorry, no, it's negative. It cannot be negative, can only be because it's measured here by the difference of those 2 numbers. And in the top left, you can see the group homophily. And if it's positive, means that you can actually have much more edges distributed within the groups greater than the relative size of the group. So this means that if it's strong, like the first 2 networks, 2016 and POCEC, A21, you can actually see that those 2 are homophilic minority. So, and then you can see there's a clear evidence of distribution in difference in exposure. The table is not only about the first 2 columns, right? So there are the second and the third column, let's say group of columns, which are basically focusing only on the nodes presenting higher degree in the graph. So let's say the ones that are already kind of popular in the graph, right? So the ones having a lot of followers or a lot of friends. So what happens in the graph for them? What happens is that if we compare the popular nodes within the 2 subsets, so still having minority versus majority, what happens is like this distribution of of exposure, this inequality in exposure is even stronger. So it means that there are this kind of this visibility is even exaggerated in the context of a small minority when this is homophilic. And this phenomenon is kind of, let's say, is not that stronger, but it's still evident also for the abs, let's say. But you can actually see that there are clear differences in disparate exposure also by recommenders. So there is collaborative filtering and SALSA. So let's say the first two in the table, which are the ones generating much more inequality for the groups. And this will be a common pattern also in the other experiments. So in network science, there is a phenomenon called rich-get-rich effect, which is actually pretty standard in the networks, which is a power law distribution in the network. It means that few nodes will have most of the, will have a huge in degree, or let's say a huge distribution, and most of the nodes will have few numbers of edges. This phenomenon is called rich-get-rich because this distribution, this inequality in distribution in a degree is even larger when the growth of the network, so along the growth of the network. And this phenomenon is even boosted by the recommender. How we can actually measure this? We use a Lorentz curve, which is a famous standard measure of inequality in economics, which is actually the more flat is this curve, the more is inequality inside the group. As you can see, we have two different lines here, the straight and the dashed lines. The dashed represent the inequality in exposure generated by the recommender system, while the straight lines represent the inequality in degree in the original graph. And as you can see, when we generate the recommendation, this inequality is even more flat, is even more close to the x-axis. The closer it is to the x-axis, the worse is for the distribution of exposure inside the group. So the red dashed line, which is always the one, let's say, the closer one, the closest to in comparison to all the others, to the x-axis, means that in the group of the minority, even if those are the one exposed more often, as you saw before, they are not all distributed, the exposure is not distributed equally inside the group, but there are a bunch of nodes getting most of the exposure. So let's say there are these super nodes, super popular nodes getting most of the exposure. And these actually increase the inequality in exposure inside the group, not only between groups, but also inside the group. So I didn't go through all the experiments of the first study because I wanted to be, let's say really a good explanation, a good starting point for the future work I'm going to present. But in summary, we wanted to show how a systematic study of disparate visibility we wanted to have a systematic study of this visibility produced by contact recommendation algorithm. Contact recommendation algorithm, people recommendation. We are talking about recommendations of users to other users. We actually saw this on real but also synthetic data set, which are not here in slides, but we can find it more. You can find it more in the paper, which is like the title you found it in the first when I introduced it. And then, as I say, homophily plays a key role. The rich-get-rich phenomena are pretty evident and are stronger when you have an homophilic minority. And also the in degree, which is the, let's say, of the nodes, which is a measure of relevance, can be, let's say, can be a component for increasing the disadvantage in terms of visibility, regardless of the level of homophily. So there are other findings that you can check on the papers, and then, as I said in the first slide, when I introduce it, you can find the title and check yourself. So, any question at this time before moving on? I'll wait these few seconds of delay, so if anyone has questions. Everything clear? Or or like everything is not clear. Okay, we can move on, I think. So next paper I'm going to present, next work I'm going to present is, let's say, a follow-up from the previous paper. Is it fun? Because like among the reviews that we got, when we got the paper accepted, one of the reviews were about, I think the study is really nice, we like it, but there is no any consideration or implication about long-term scenarios. And we say, yes, that's true. Let's investigate that. Let's do research on this. And then now it is like the second paper came out, which will be, I'll presenting it in a, let's say, even like 10 days, couple of weeks in Atlanta. Is actually the same conference as before, the ICWSM, which is a premium conference in computational social science and data science. And it's about understanding the long-term effects of people recommended system on the exposure. So still we'll talk about exposure inequality, but in this time in long-term effects. It's a joint work between me and like my two advisors and a master student, Maria Luisa. So in the previous work, we were talking about this static picture, right? So of having these recommendations generated in a one-shot, so this output generated in one-shot recommendation. So we're having this social network given some input characteristics, and then like pass it to the link recommender to generate the output. But we didn't have, so we had a static picture of what was going on at the level of recommendations, right? So with no implications, with no consideration of the long term. So the next step was to include user feedback. As you may wonder, some user may actually accept or reject recommendation depending on the relevance or the way they decide to behave in the graph. So the consideration, the next question about including the user feedback in the pipeline will be: is it happening that is there any long-term consequence of having this homophily on the table? So is there any long-term consideration that to do about the effects of the recommended system? In this specific case, we are talking about the feedback loop. So these kind of circle that like this process that iterates many times. So you have a user in the graph that gets some recommendation, accepts some other, and then gets new ones. It's called feedback loop. So using the recommendation accepted by the user as a new input for the training of the algorithm. So this feedback loop was our focus for the study. And what we did here, we proposed a simulation model to understand how the long-term impact of interaction between the initial network, the recommendation algorithms, and the user behavior. So these three components were the main players in our simulation study. So as I say, there are three different components. There is the social network, which is here, which is basically a semi-synthetic. So what we do here, since we want to include a social network, we want to propose a simulation model, everything can be parameterized, let's say. And specifically, we're starting from an original network, so we can actually build semi-synthetic data. So as I said before, minority and majority partition, let's say, and the level of homophily are the two crucial components in our network, right? And what we did here, we proposed a model for tracking the level of homophily and the distribution of majority minority inside the network. So we have a method that do links rewiring. Don't forget this term because it will come out later. which means that we don't change the source of the edge, or we change the destination. So we change the destination of an existing link to another for let's say reducing or increasing the level of homophily. And also we do node class swapping, in the sense that we want to be sure that there are like a specific number of red and blue nodes. We just change the color of them. In this way, what we do is, like, without changing too much the structure of the original network, we can actually generate different configurations of homophily and majority minority. So starting from the original, which is actually one of the 20 that I saw before we presented before, we can have 4 different configurations, and where each one has a particular characteristic. So we have an homophilic minority, one homophilic group about the same size. Then we have heterophilic minority, something we never saw before, and 2 homophilic groups. So having this synthetic generation also answer to the question is, can we answer to scenarios that we never observed in the graph, in the social networks that we have, in the real social networks that we have? The answer is yes, because in this way we can generate semi-synthetic network, even new from us, like for us new, and so never experienced it in real life. So as I said, there are 3 components, right? So there is the social network, the recommendations, and the user behavior. The recommendations are pretty the same. Recommendation model are the same as before, so we don't really change those. I remember, like, as I said, Amicadar, alternatively square, salsa, this stochastic approach, and then there is a baseline. Then this is like the novelty of our model, which is about including the user behavior models inside our pipeline. So when we generate new recommendation, now the user can accept or reject some of those. And this policy, like, we don't have only one policy. We decide to have 4 different ones actually, where the first 3, each one sticks to an homogeneous behavior of the user, and the 4th one is a mix of the first 3. Specifically, we have the lazy policy, the lazy behavior, when the user accepts directly the first recommendation, no matter what. So relying completely on the recommender. Then there is the opposite, let's say, policy, the opposite behavior, where the users choose completely at random one of the recommendations suggested to him. And then there is the position bias one, so which is like, let's say, the one in the middle between those 2, which is actually the most reasonable one. And still, the position bias I was mentioning before comes out again, which is about where the user may actually accept or reject the recommendation with a probability proportional to the position of the item. So we don't accept directly the first recommendation, but we sample one of the recommendations submitted of the user proportionally to the position. And then to test if having this homogeneous behavior may actually affect the final performance, we have also the behavior mix, which is a combination of the 3 policies. This means the combination means that each time a user first picks, like, I mean, user can change the way it behaves at each iteration. It's important here to find out that, like, we don't have natural growth in our model, simulation model. We just focus on the recommendation, the links created by the user. Is it true that every day, like, we can accept and remove friendships coming naturally? So a friend can follow us even without recommendation. We can actually remove friends that we follow, like we remove the follow naturally. We don't need the recommendations. But in this case, we don't have those interactions. We don't have natural interactions. We just focus on the interaction stimulated by the recommender. So, and nothing related to the natural growth is included. So first result, which is the first important result, which is actually probably a consequence of what we saw before. If we track at each iteration, so we iterate this process multiple times, right? We iterate this simulation multiple times. We generate a bunch of recommendations. Some users accept, some users reject. Then we augment the graph because the one accepted, the recommendation accepted, are now part of the original graph. And then we generate again the recommendation. So we train again the recommendation and so on and so forth. So each iteration, we can access to a new bunch of recommendations. What we experience is that homophily is a key player also in the long term. Specifically, So how do we read these plots on the right is pretty important. So please stop me if it's not clear. So what we do here, we track the exposure of the minority. And as I told you before, some of the minorities here are homophilic, some are not. Specifically, G1, G2, and G4 are characterized by, as you can say, going back here, G1, homophilic minority, G2, homophilic minority, and G4, both of them are homophilic, so even more interesting, are characterized by homophilic minority. So the question here will be, what happens to each, so what happens to the exposure of the groups in the iteration? So we track here exposure of the minority, but this is actually, let's say, complementary to the exposure of the majority, right? So what we see here, what we experience here is that the exposure of the minority is in basically 3 over 4 cases more, let's say, is over the dashed line. Dashed line represents the size of the minority in the graph. So in all those cases, exposure received by the minority is much more stronger than its relative size. And as you can see here, specifically in G1, G2, and G4, the exposure grows over time. Consistently with all recommenders. Some recommenders, it grows less, some recommenders, it grows more. But specifically in all cases, we do see that the exposure is growing over each iteration. So in the x-axis, we don't track only the number of iterations, right? So, but we actually track, so each dot in the lines represent an iteration, right? And those 4 lines are the recommender systems, as I said before. But in each time, in the x-axis, we are tracking the number of edges we added starting from the original graph. So 10, 20, 30, 40, 50, and 60 represent basically the number, the relative size of edges increased starting from iteration 0. So like when we arrive at the end, we had just added 60% more of the original graph. Okay, and in all these cases, as you can see, if the minority is homophilic, there is a boost in exposure in the long term. So this boost is not constant, right? And also on the other case, we can actually argue that when the minority is not homophilic and it's the majority being homophilic, like G3, as I say, G3 has an heterophilic minority, a completely opposite scenario. So doesn't want to connect to their peers, but they connect to the other side. These exposures slowly decrease. And so what we can actually argue is that actually exposure is not, let's say, distribution of exposure over time is not homogeneous among recommenders. Indeed, as you here, we basically zoom in on 2 recommenders, ALS, so alternative least square, the collaborative filtering one, and the SALSA. And you can see that there is a sort of steady state in a steady state phase. So that means that, like in the first iterations, the exposure grows significantly, but then it starts to be stable. So it's not growing linearly. Sometimes it happens actually. So for example, in G1, but if we look at G4, D and G0 for ALS, this growth is a steady state, goes through a steady state. Why in SALSA, the growth is linear. So depending on the recommender systems, we may actually have different behaviors in the long term. So it's not that trivial to say, the recommender system increase exposure in the long term for the minority. That's true, but it's actually depending on the type of recommendations. And this is actually one of the most interesting results is the following. Even if both of them are homophilic, at the end of the day, the one that will benefit will be the minority. So even if both of them are homophilic, being homophilic as a majority is not that good as being homophilic as a minority. Because G4 is a configuration when both of them are homophilic. Now, with the aim of disentangling, so disentangling can be done because we are synthetic data set, we generate a wider set of configuration of initial network. And we track E. E here on the x-axis is EMM, is the relative size of the edges. So we just count how many edges there are in the minority over the total number of edges connecting the minority. So we count each time we count at the numerator the number of edges connecting to nodes belonging to the minority, and at the denominator the number of edges belonging to the number of edges which at least one of the two is connecting to the minority. So what happens here, we can see through these heat maps that homophily and relative size contribute differently to the final growth. Specifically, that the homophily of the minority impact the speed. So let's say that the stronger is the homophily of the initial homophily, faster will go the growth in terms of exposure. But then the relative size impact the severity. So this is happening. We can actually see it through the heat map because of the color here, right? So the severity of this effect is mostly determined by the size of the minority. So it's good that through the synthetic data set we can decouple the effects. So going briefly to also other important results connected to the rich get richer effect that we saw before. In the long term, we have still individual inequality, not only groups, because inside each group, we track here the Gini coefficient. The Gini coefficient is still here, another measure coming from economics that wants to measure the level of inequality inside a group. So let's say level of inequality of, let's say, distribution of some quantities over in a subset of group. What you can see here is that for all the network, we can observe a richer effect in both cases. So the networks are actually, depending on the recommendations, we can have a boost in terms of inequality in degree in the graph. This in degree is basically tracked in the augmented graph. So we only with the feedback loop, we just look at the new graph. We just the new graph, and each time the Gini coefficient increase. Specifically, still, we want to, since we have a synthetic distribution of the graph, we can focus on many different configurations. And the most interesting one is that even when the minority is the heterophilic, the group which is impacted more is the majority. So we have an indirect effect of inequality of one group to the other. So being heterophilic may actually have a consequence of the other group, even if the other group is not presenting any particular behavior, because the positive trend of the Gini index is kind of faster, no? It's stronger in the right side. So I shown that like at the individual level, what was happening for the nodes in the graph, we actually say, okay, but is it possible to track the same information at the level of recommendation, not at the augmented graph? Because the question is, if the graph changes, also the recommendation will change. How do they do? How do they change? And this question is actually connected to something that we saw before in the Lorentz curve in the first paper, which is basically that if we track the exposure accumulated by nodes ordered by their in degree, we will see that after few iterations, we will have in presence of homophilic or heterophilic behavior, so in presence of strong bias network distribution, we will have these super nodes in the recommendation output. You will see that the yellow bars are kind of predominant at some point, right? After iteration 10, most of the nodes recommended by the algorithms will be always the same, because will be only the nodes belonging to the first 1% of the in degree in the group. It means that no matter if you're a minority or a majority, only few nodes will be recommended at some point. So there will be the sort of these super huge nodes recommended all together in the graph. It's still like, even when the graph is heterophilic or homophilic, this is a subset of nodes that receive most of the exposure produced, as you can see here in the two plots. So to sum up, to wrap up, like in both cases, we have like these two, let's say, different situations, which are like kind of analogous. Like there is one which is a network, and one which is the recommendations. And at the end of the day, a small subset benefits in long term more and more the injection of new links generated by the recommender. Now we enter in the last paper, which is, so all the insight that we grasped from the first two are actually useful and for the last work. And the last work is about rewarding what to watch next recommendation to reduce radicalization pathways. So in the first two works, we have been actually seeing techniques for characterizing an effect. Now we actually don't only characterize but mitigate. And how we do it, we do it grasping some insight from the first two papers. So through characterizing some phenomena in other contexts, we can actually generate algorithms here that can stick to concept we saw before, which is about exposure. So this paper has been presented a few weeks ago, in the end of April, in the most important conference related to the web. So it's called the Web Conference. Before was called WWW, which is actually the fundamental conference when the work about the web is published. And long story short, it was actually a successful story because we won the best paper award in this conference out of 1,800 submissions. So we're pretty happy and honored to receive this award, and we actually won the best paper award of this of this conference. So because of this work, and this was the super team that was collaborating with me. So my two advisors and collaborators from China and Helsinki. So what's the paper is about? So as I say, there's the what to watch next recommenders are a type of recommendation, sequential recommendation with a key features in video sharing platforms, because what they do, for example, in YouTube, they sustain user engagement and increasing the content views along the way. So the more the user keep to be engaged with the platform, the more increase views, it stimulates advertisement. It's a key feature, okay, specifically for online social platforms. Recent studies have been showing that, so characterizing the phenomenon, have been showing that this what to watch recommender plays a key role in driving users towards undesired content. And undecided. What does it mean undecided? In this case, we talk about radicalized content. So what we experiencing in YouTube specifically is that the recommender system was trying to drive the users to radicalized contents, even if radicalized means having a political leaning really towards the extreme of right or left wings. So driving the user toward this right or left radicalized content, even if the user was not supposed to be radicalized himself. So this happens because some of the users in the training data may actually interact much more often with this radicalized content because they are sticking to those ideals. And what happens is a user which is kind of neutral may actually be driven by the algorithm to inside some rabbit holes, specifically in some radicalization pathways. So what may happen is if we know that a bunch of videos are radicalized, what has been experienced in YouTube is the user gets stuck in those radicalized contents because of the recommendations. So there are some areas where the recommendations are driving the user, that the user will experience only radicalized content. So what we do here, we want to devise algorithms able to mitigate those radicalization in recommendations. How we do that? We use graphs, and we will see later how do we do it. But so since the graph came out again in this case to solve an a challenging problem, and in this case we will not talk about graph of users, but we can talk about graph of contents. So please, since probably this is the most technical part, please stop me at any time if it's not clear. Okay, I will be happy to answer the questions. Okay, I guess we can start. So if we consider a set V of videos inside our platforms, of n videos in our platform, when at each video for a user is associated as a sort of score that corresponds to the relevance or level of personalization for the video V. We can actually think about this score as a sort of the probability score, the relevance of the video V, given that the user have watched the video U. So what we actually do, we can generate for all the possible videos the user could watch a subset of list of recommendations, which is pretty reasonable, right? Because in YouTube, no matter where we are in the graph, no matter where we are in the platform, if we start to watch a video, there will always be a subset of video recommended after the initial video watched. So what we can do, we can actually do the same. We can assume that there is the recommendation of video B, recommendation of video starting from you that are ordered by relevance, this relevance S. And from this relevance, we can actually think about the probability. So like we can actually given the position of the user, so given the score, we can have a position of the users inside the graph and inside the recommendation. And given the position, we can actually derive a probability. Position I, we can derive probability UV, which is the probability of jumping to the video V, given the fact we watch the video U. And this probability is given by the position of the video in the ranking list. So what we do, we actually, since we can map for each possible video, sorry. We can actually map for each possible video a subset of recommendations. What we do, we generate a graph where each node is a possible video watched by the user, and the other edges are all the possible recommendations where the user will be driven through by the recommenders. So we are trying to reproduce, let's say, try to have a proper formulation that reproduces these radicalization pathways. So if we have this graph of videos and a user jump from a video to the other because there is a recommendation. So this graph represents the future of the interactions of the user with the platform, right? So this graph is for one single user. What we can say is like, okay, this is super fine, and like it's kind of a standard. I will not say standard for the videos, but let's say having a connection between contents derived by the interactions. But what we can say later is that are some videos, let's say, different from others? The answer is yes, because as we say, some videos can be labeled as radicalized, as harmful, let's say. And those are the video VH, H for harmful, and the rest are called neutral. That will be a subset of users that will be recommended as called radicalized, and the VN will be neutral. So what you can actually do, we can actually quantify the future exposure associated to this video harmful. So the bias that may exist here is inside the graph. So all the information that we grasped in the previous paper help us to define here, which is the bias in the graph of contents. And this specific case in the bias in the possible way of the user may interact with the video. So it's still the exposure quantified for the radicalized videos. We are almost there because at this point, as I say, the goal is to reduce the segregation inside the recommendation graph. And this radicalization is generated, the radicalization pathways are generated by the radicalized videos. Means that we can actually define a score called segregation score. This segregation score represents the number of steps for a radicalized node U needed to reach a neutral one. So for each radicalized video, we can actually quantify the number of videos we will watch still radicalized before jumping to another neutral one. It's a sort of quantification of how many videos I will watch again before going out from this radicalization, radicalized pathways. Now, we can assume that we have different discourse for each radicalized video. What we're actually interested in is mitigating the maximum, so reducing the maximum radicalization pathways. How we do that? We do that through an edge rewiring. The edge rewiring is this operation when we actually modify, so the rewiring is a term I was using before, we modify the final, the distribution of the recommendation given to the user. We modify the destination, so removing an edge between two radicalized videos and directing this edge towards a non-radicalized one. How we do that? We want to generate we want to find out a set of rewiring operation O to reduce ZG, which is the radicalization of the graph. To do that, we have of course we have a trade-off, because each time we do a rewiring, we reduce the quality of the initial recommendation which were the best based on the score S. So what we do here, we reduce, given a probabilistic graph, what we actually do, we want to track the quality of the, we want to be sure that we reduce the radicalization without losing too much in quality. Well, how we do be sure about that? We have an input parameter tau that tracks this loss is expressed in terms of NDCG, which is a metric of quality of recommendations. So at the end of the day, we will apply K rewirings for reducing the segregation inside our graph. How do we do that? We use absorbing random walks. These powerful methods, like this powerful type of random walks, that we can actually quantify the actual segregation and expected length of the path between coming out from the radicalized to a neutral node. In this way, using radicalized and absorbing random walk without losing too much on the details, the technical details you can find out on the paper, we are able to devise two algorithms. And specifically, we have the optimal rewiring and the heuristic rewiring, which are the optimal rewiring is the algorithm one, which is able to find which is the optimal rewiring operation for reducing radicalization in one shot. But also then there is extension to the case. So because the first algorithm solved the problem for one rewiring. But if you want to apply the K rewiring, we use a heuristic. You applying K rewiring, running K times the optimal algorithm one. So algorithm 2 runs K times algorithm 1, you applying some future engineering along the way to reduce the problem. So in the final result, what we see in the results, we see that this radicalization, reducing radicalization algorithm for reducing the radicalization are actually effective. And in few iterations, we are able to reducing the initial radicalization. In this case, Z0 represent the initial value, ZT represent the value along the way with different Ks. And when we reach more or less 30 or 40 iterations of the algorithm, so after 30 rewirings, we are able to reduce dramatically the initial segregation value. And this is true for datasets coming from YouTube and also for datasets coming from news recommendation. Why news recommendation? Because actually, this is not a problem that may actually affect only the videos we want to watch, but also the news we want to read. So assuming that we have a subset of news that we know are unreliable coming from sources which are not so reliable, we may actually bias the point of view of the user, keeping to recommending, let's say, to recommend bad quality or let's say unreliable news. So this segregation comes out also in the case of news recommendations and still is effective no matter which is the data set. Also, we actually saw that in the second line of plots here, we track the different quality constraints, the algorithm is still effective, and we are able to reduce dramatically the radicalization even if the tau has different values. So as to give you an understanding, the stronger is the tau, so the bigger is the tau, the small will be the subset of possible rewiring because we don't want to lose too much in quality. But these results show that even if we increase the tau so much, we still be able to generate a reduction in radicalization. So what's next? So to conclude, to wrap up, since actually like only 10 minutes are left, I'm open to question and like a discussion in this case. What's next? We saw that with empirical evaluation, but also synthetic dataset, it's possible to characterize short and long-term behavior of specifically in people recommender system. And we saw how we can investigate through the simulations, human bias is the feedback loop. And showing that different sizes and behavior, we have different effects. And some algorithms are better, some algorithms are worse to stimulate these disparate exposure. We are not done yet because we need simulation models able to be dynamic, because user can change their tastes and preferences along the way. And we actually need more enriched data set. We need more metadata. We need to know the natural growth of the data set. Actually, we need to incorporate more sophisticated models. So the job is not done yet. For the graph data, so all the other line of work about the graph data, we may actually see that this definition of segregation introduced in the last paper is pretty general, so it can be applied to many different applications and can actually be slightly modified. And so, for example, for quantifying the reachability of the items, not the segregation, but also the discoverability of the diversity of the output. So this measure opens to really many different follow-ups when we want to still interested to quantify this algorithmic bias in exposure. And this choice, of course, depends on different domains. And we can think about segregation by popularity, for example. So check if the popular items are as less segregated, how much this effect exists for less popular artists, for example, in playlist or generation in streaming services, or for example, mixing this definition with unfairness, so understanding if there is a possibility to be unfair for some groups inside the recommendations in terms of exposure. So some groups characterized by some demographics can actually be less reachable because of the structure of the data set. But then also there is actually more to do in the level of the algorithm. So we can actually build interpretable models to give to the user the chance to select recommendations that stick to definition of relevance, but also less segregated. And also this algorithm, as I said, is a post-processing. It's clear post-processing that we want to aim to having an in-processing. So having an algorithm able to reduce radicalization along the way. And yes, I guess that's it. I'm done. Thank you for the attention and the patience to follow me into this 2 hours, like 2 hours journey in algorithmic bias. And now I'm open to questions, curiosity, anything else. And as I say, you can still reach me at these contact information on Twitter or on email. I would be happy to answer. Adversarial behavior in this domain. That's a good point. That's a good point. And yeah, no, I will say that as a follow-up, probably probably there will be a tracking, a characterization of the of users online, right? So understanding, for example, if depending on new contents, the user may actually interact, like it will be actually a peak of interaction, right? So yeah, that's a good point. Like probably the next actually the follow-up will be trying to characterize those effects on real time. So trying and tracking the information generated by the user, and when a new content by a radicalized channel, for example, comes out, and see how the radicalization is generated by the algorithm. I hope my algorithm is able to still generate a reduction in radicalization, even in a dynamic setting. But I do believe that in that case, probably there should be another problem formulation. Problem formulation, assuming the recommendation comes in batches and not all together. So we have partial information available each time we generate, let's say, we generate a less segregated output. It will be much more complex to devise as an algorithmic scenario. Thank you, Christian, for the question, by the way. As I said before, the slides will be available online also later. So, and the talk also is registered, so everything will be there. Any other question? I don't know, like by anyone, someone else. Okay, so I guess we can wrap up here if there are no more questions. And thanks everyone for attending. And yes, feel free to drop any questions by email on Twitter if you have any. Thank you.